Hello and welcome. My name is Aidan Boyd, and today I'm presenting the paper Human-Aided Saliency Maps Improve Generalization of Deep Learning. And this work was conducted at the University of Notre Dame. And the idea for this work was we're trying to collect human salience information for correct classifications and try to incorporate that directly into the deep learning process. And we want to do this in an architecture agnostic way, such that any network can be used. We also then apply this to iris presentation attack detection, where you're trying to guess whether it's a real iris or a spoof or a fake iris. And we set it up in three scenarios, S1, S2, and S3, where S1 is the traditional deep learning method of just having a lot of data and applying it to the neural network. S2 is the opposite, where we have very limited data. So in S1, we have about 450,000 images, whereas in S2, we have about 750. And then S3, we take this limited data and collect human annotations on it. So we ask humans to mark off salient regions that led to their classification decision about that sample. And what we do is we perform a transformation to the data and then retrain on it. So we train S1, S2, and S3 all in the same manner, and then just evaluate the performance differences. We do this in open set style, where we have 7 attack types and we train on 6 and then test on the 7th, simulating an open set. Leave one attack type out, unseen data testing, and then we compare it to a recent competition of live detection. So this is the tool that was developed to collect the data, and first users were asked to identify the nature, whether it was a live iris or one of the 7 spoof types, and then they have to mark off at least 5 regions in that image that led them to that classification decision. So in this case, it's a textured contact lens, and the green highlighted regions are the areas that this person thought were salient in the image for that classification decision. And what we do is we transform the data in such a way to incorporate this. So here we have on the left, we have just the regular sample unaltered, and then we have 5 correct classifications from this sample saying that it is a glass artificial eye, which it is. And then in the bottom right, we combine them all together to create the human saliency map. And here we have a heat map representation where blue corresponds to unannotated regions, and the closer it gets to red corresponds to more annotations. And what we do is we apply this saliency map to the training data such that we inversely proportionally blur the image in the regions based on the number of annotations. So the least annotated regions will be blurred more than the most annotated regions, and unannotated regions will be blurred with a maximal value. And we have 8 maximal values, and we combine them all together. So this sigma max is denoted to the region of unannotated. So unannotated regions will be blurred with this, and then it's a function based on a function on how much, and based on how many other people have annotated it, based on how much, that'll determine how much blurring is in that region. So the one with the most annotations will be unchanged from the original. So we're trying to suppress human-defined unuseful information and classification. What we found is this is actually protecting us from overfitting. So here we have S2 and S3, which is the limited data, and then the limited data plus human annotations. And what we see in all 8 cases here is that the training accuracy goes to 1 pretty quickly, so 100%. But in the case of S2, which is just the limited data, the validation accuracy, which is from the same source, is roughly around 50 or 60%, which is almost random chance. Whereas the S3, which is just the same data as S2, but with the human annotations, is about 80 to 90%. So the improvement in validation accuracy is quite large. So we see that this is protecting us against the overfitting, considering that this is the same validation set in both cases. So in the results, we see that the S1 is the best. So having most data is optimal. However, what's interesting is that S2, which is just a small data set, the performance is so much worse. The degradation is quite severe in this case. And then what we see is S3, which is the human annotated data. This bridges the gap between the two. We're getting closer to this S1, which is the same amount of data samples that is in S2. So this is a very cool result. When we compare it to the competition from the LiveDet 2020 competition, we see that our method S3 would have won the competition and would have just narrowly lost to this S1, which we just saw was better. But what's interesting is that S2, just a limited data, would have come 3rd in the competition. So clearly this human annotation is providing a lot of value. So with that, I welcome any questions. I'm looking forward to hearing from you. Thank you.